Hi guys, welcome back to Physics 145, Chapter 9, Part 2. For this part, we're going to look at AC, okay? So now this one I will call 9.2. This is a AC, okay? AC circuit or alternating circuit. Right? Alternating current circuit. Alright, now what is alternating current? Well, alternating current generally is a current that flow in both directions in a closed circuit. Okay, in a closed circuit. So it's opposite. It's not really opposite. It's actually more complicated than the DC current. Okay, so now the short form for this will be I'll use simply AC. Yeah? So now I give you example of the type of AC. Okay, AC can have so many types. Okay, I draw the axis first. So this horizontal is a time axis, and then the vertical is the AC voltage. Okay, the AC voltage. Now the normal AC voltage that we use in our house is a sinusoidal AC voltage, so it looks like this. Okay, so that is the AC voltage that we have. All right, so the house one, this maximum value is given by roughly 340 volt, negative 340 volt maximum. But when you calculate the root mean square value is 240, all right? And then the frequency is 50 hertz, okay? And that means this value here is 0.02 seconds, all right? So that is our AC, but the 50 hertz is depends on the country. Yeah? Our country is 50 hertz, and then United States will be 60 hertz, and some area have combination of 50 and 60. So now that is example of AC, which is a sinusoidal type. It's a smooth AC, but our AC can be something that looks like this also. Okay, something that looks like this. For example, here, right? This is also AC, but this AC is a triangulation AC. Okay, triangle AC. This one also AC, example of AC, because positive, negative, right? Now another one is if you went to hospital before, you see patient lying down on the bed with a body hooked up like an Iron Man, and then there is a monitor to check the pressure, the heartbeat, and so on, right? And then you see things like this happen. Okay, and it come with sound some more, right? So see that? That is a pattern of the heartbeat. This one is an AC signal. Okay, AC signal, except the voltage here will be very small, maybe just 10-20 millivolt. Okay, depends on the body. All right, so this example AC, and then our voice, when you speak into a microphone, which convert your sound energy into electrical energy, is more or less like this also. Okay, so this is an example of AC, which flow in both direction, to and fro. Okay, so our house is AC. Okay, our house is AC. So why we use AC in the first place? AC is the basic electricity used by transformer. Okay, so your transformer is used to step up and step down the voltage. So whenever power supply, okay, need to be sent to a far away places, we normally increase the voltage by stepping up. And that one can only be done on AC. DC cannot. Okay, but by the time it reach your house, all your computer, a lot of gadgets are function in a circuit board based on DC. So then you have to convert back to DC again. So that is how they are actually related to each other. Okay, that doesn't mean that AC more important than DC. No such thing. Eh? So both are important. All right. So the next one is in these AC circuits, as I said just now. If you look at the oscilloscope, our AC circuits, our AC power supply looks like this. The maximum is 240. Then, where does that 240 volt come from? Okay, so that is a new concept now. So our new concept is what is the meaning of the root mean square voltage? Okay, root mean square value. Right. So the next one is our root mean square. Okay, root mean square value or root mean square voltage. You can apply the same thing to root mean square current as well. So the symbol for our root mean square voltage is simply V root mean square, RMS. Okay, RMS. So that means, okay, the meaning of this one is this. Yeah, so V root mean square of an AC supply is the equivalent, okay, equivalent DC voltage that will give the same heating effect. Okay, that will give the same heating effect. Now, for example, we start with a imaginative experiment. Let's say you have a AC power supply used to heat up some liquid. Okay, we choose water here. Okay, and to heat up something, you need to have some heater. Okay, and this heater, and then you have a beaker with water. Okay, beaker with water. So this water is this amount. All right. Now let's assume that this waveform here, AC waveform, have something that looks like this. All right. So your waveform is sinusoidal. Okay, sinusoidal. And let's choose the waveform maximum value to be, let's say, 340 volt. Okay, and this one here is negative 340 volt. These are AC waveform, and this is a time axis. So let's assume your initial temperature of water, okay, the TI, the initial temperature is, let's say, 24 degrees Celsius. Like now in the aircon room is 24 degrees Celsius. Now what we want is, we want the temperature to increase to, let's say, a final temperature of let's say 34 degrees Celsius. All right, and let's say it takes a time of, okay, the time needed, T, is, let's say 5 minutes. Okay, 5 minutes. All right, so that is what we have. The initial experiment number 1 using AC. Then suddenly your AC power supply gone. Okay, your AC power supply gone. Then you have to repeat the same thing again. Now, if you look at the waveform, you have 340 volt. Okay, so you might think that, well, I just replace a DC of 340 volt, but it actually don't work that way. Yeah? So you have to do some calculation on that, and that's why the root mean square is important. So now, when we change to DC, let's imagine that because the AC power supply failed, so we switch to DC. Okay. Of course, if you switch to DC, I believe the battery, the number of battery will be a lot. Okay, will be a lot. But of course, it definitely does not need go up to exactly 340 volt. Okay, let's imagine that we have a power supply that can change. This is our DC power supply. Okay, variable DC supply. Okay, now using exactly the same setup. Okay, everything the same here. And then you have the same beaker with the same amount of water at initially the same temperature. Okay, the same temperature initially. So our water here, okay, with the same initial temperature of 24 degrees Celsius, and then the final temperature that we need is 34 degrees Celsius. And if we want it to be able to reach the temperature in the same amount of time, then we know that this DC's power supply must supply the same amount of energy like the one supplied by our DC, by our AC here, right? So how do you do that? So first you look at by comparison. Okay, what the question is, what voltage do you need? Okay, is it 340? Then we compare the graph by looking at who has a larger surface area. Okay, who has a larger surface area? So first we have this AC. Let's assume that that is the height of the graph. Okay, this one, and we will draw, let's say, another one is for the DC, and let's say in the same amount of time here. Okay, in the same amount of time, but we just leave the time alone first. So now this is our AC, VAC, and this is our VDC. Now our graph for AC is like this. So we draw two here, just to show you the cycle. Now this one is an area below the graph. Okay, the easiest thing to compare is like this, and then we have a power supply of DC. Now let's assume in the same amount of time we want to compare who has a larger surface area. Okay, so now our DC should be something that looks like this, a constant VC, right? So this is the area here. Okay, this is the area. Now if you look at our value, the one that we have just now, 340, and this one is negative 340. So our area here, I will call this one area, the total area here, 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 and here. All this total area I will call AC. And for this one, the area I will call ADC. Now, if you choose this one to be 340 in the same amount of time, T prime, definitely this ADC is larger. Okay, so you see, if VDC is equivalent to 340 volt, that means the conclusion will be ADC surface area here will be larger than the surface area of the AC. So what does that mean? That means that the energy supply by the DC is more than the energy supply for the AC. So that means if you use the same voltage replacing this one by 340 volts, so that means you choose 340 volt DC, your area larger, that means supply more energy. In the same amount of time, 5 minutes, you're going to heat up more than 34 degrees Celsius. So that means they are the same value of the voltage does not mean they have to carry the same amount of energy. So to do that, we need to reduce this 340 volt. So now, if VDC is less than 340 volt, then your DAC have the possibility of equal to the area of this one. Okay, so that means conclusion is the energy supplied by the DC has a possibility to equal to the AC, the energy supplied by the AC. So what we do is we reduce this voltage. Okay, we reduce this voltage here to a certain value that, according to mathematics, is called the root mean square voltage. So to get EDC exactly the same like this one, so the area must be exactly the same. So to get exactly the same, your voltage, okay, the voltage of the DC is equal to the maximum voltage of the AC divided by square root 2. Alright, so that means this value here is called the root mean square, and this one is the V root mean square. See or not? So we calculate, see what happened here. Our V root mean square is equal to our peak voltage now, 340, right? 340. So you divide by square root 2. See what do we get here? 340 divided by square root 2. Okay, 240. There you got 240 volt DC. Okay, so you can use DC 240 volt to replace that power supply. Alright, so that's the meaning of your house 240 volts. So in actual case, the maximum voltage in your house is 340, but when come to equivalent DC voltage, it is 240 volt only. Alright, so that means to calculate, okay, our formula is this one. Okay, this is our formula to calculate the root mean square voltage. So root mean square voltage, the same formula can apply also to root mean square current. Okay, for example, you have 10 ampere, you want 10 ampere maximum, so you want to calculate the equivalent DC current, then you can just divide that 10 by square root 2. Okay, you have got less than that, about 8 point something. All right, so that is our root mean square voltage, which is important in AC. All right, so that is the first one. Next one is we want to introduce all the components that you have already learned, except inductor that you have not learned yet. Capacitor, I believe capacitor also not in your syllabus in the first place. Alright, but never mind, we will look at the job of all that component one by one, okay, and then we put them into our AC circuit. Okay, first component in circuit. What component do we have in circuit? Okay, so look at them one by one. Yeah, so the first one is, of course, resistor. Then the first one is resistor, has a resistance R. So what's the purpose of resistance? Okay, the purpose is to control the magnitude of current. Okay, it is used to control the magnitude of current. Sometimes we use the word resist, but not all the time we resist them, we control them. Okay, of course, you control by resisting the flow of charge. Okay, so it's better to use the word control the current flow. All right, so any changes or not if we use it in AC or DC? Okay, the characteristic. Okay, the characteristic, we look at the characteristic. Okay, so the characteristic is like this, no different. Okay, no different in its resistance. Okay, okay, no different in its resistance when put in DC or AC. That is the resistor. No different whatsoever the value of resistance. For example, if you have the resistor of 10 ohms, you run it in DC and you run it in AC, it gives you the same effect. Okay, no changes, right? So that's the first one, resistor. So the unit will be in ohms, right? Okay, the unit for resistor in ohms here. Next one, number 2 is capacitor. Now, what is capacitor doing? Capacitor have a symbol C, and a value, its value is called capacitance. So the purpose, okay, to store charge or electric field, to store charge and also to release charge. Okay, but there is another device that have the same effect, right? So something like battery, store charge, release charge. But the difference between battery and a capacitor is actually storing charge and releasing charge at higher speed. Okay, in a shorter amount of time. Okay, in a shorter time, right? Okay, it happens in a very short time. Okay, very short time. Alright, so that is the difference between capacitor and resistor. Now, how about the characteristic? Now, the characteristic of capacitor is much more interesting than resistor. So, number 1, capacitor will stop the flow of DC current when it is fully charged. Okay, when it is fully charged. See, when it is fully charged, current stops. So it is used to block DC actually. Okay, so that's number 1. Number 2, capacitor allow AC current to flow. Okay, it allows AC, when you change direction, just charge this, and so on. So it seems like it allows current to flow for AC. That is the beauty about capacitor. And then for the capacitance, the unit for capacitor is capacitance is farad. Okay, F-A-R-A-D. That one is something to do with the name of the scientist called Michael Faraday. Okay, Michael Faraday. All right. Now the next one is number 3, C. This one will be the inductor. You know inductor? Inductor have a symbol L. Inductor is actually a solenoid. Okay, a solenoid with a coil with like a spring, right? Something like this. So, oh, I forgot to tell you. The symbol for resistor is like this. Symbol for capacitor, more or less like a battery except same length. And the symbol for inductor is a coil. Okay, a coil, right? Now we look at the purpose of inductor. This one is to store magnetic field and release magnetic field. Okay, store magnetic field and also to release magnetic field. So that is what the inductor is doing. Now the characteristic. Okay, characteristic number 1 is inductor allow. Okay, inductor allows DC to flow through. Okay, to flow through and just act like a electromagnet. That's it. And then number 2, inductor also allow. Okay, also allow AC to flow through. But now it acts as a signal filter. It's actually same like capacitor. They filter things. Okay, they filter things. Alright, so the unit for inductance will be Henry, H. Okay, Henry. Alright. So that is the introduction for the components that we normally use in our circuits. Okay. So the circuit that we the component other than this, there might be something else like diodes. Okay. And then for example transistor, op-amp and so on, but those are not in your syllabus. Alright. So now the next thing is we are going to look at what happens when we connect. Okay, when we connect all these resistor, capacitor and inductor separately one by one to what we call it, to an AC circuit. Okay, so we look at connection of R, C and L to AC circuit. Okay, what happens when we connect them separately and then we also connect them all together. We'll see what happens. So the first one is R in AC circuit. Okay, we're going to see what happens when in R in AC circuit. So when you connect R in an AC circuit, okay, the resistor symbol, okay, like that. So definitely current will pass through, right? Okay, so this one is our voltage. You already learned wave. So since this one is a wave, you already know this is something that looks like this, omega t, right? Okay, and then the current here also changing according to this. Okay, the current also changing according to this one here. So your resistor R, if you connect a voltmeter across a resistor, you can actually measure that the voltage across this one is actually equal to this, okay, IR, okay, IR. But of course we are talking about root mean square here, all right? So this is I. So if you talk about root mean square value, okay, then it seems like follow Ohm's law, okay, or follow Ohm's law. Whether it's AC or DC, they are the same, okay, they are the same. So this one no changes. So in this case, we discover something, okay, we discover something. Of course, the theory is very long about this, so we're going to look at how are we going to get that theory. Okay, so the theory is like this. If you are asked to find the current here, how are we going to find it? So we assume something like this. Okay, so this is A, B, C, D. Okay, A, B, C, D. So there is a law that I'm not sure you didn't study that law in the first place in your syllabus, I think it has been taken away, which is called the Kirchhoff law. Okay, Kirchhoff law is actually important to understand this one. But anyway, I'm going to show you the Kirchhoff law, but it's not necessary for you to use that one in the exam, because it's not going to come out in the exam. So now our Kirchhoff law states that if you go around the circuit, the total change in your potential will be 0. Okay, so we assume something like this now. So we assume this is positive, negative initially. So we're going to start our journey from A to B, B to C, C to D, D to A. So you look at this current flow from positive to negative at this moment, right? So that means it's going to go through the resistor from D to C. So we start from A to B. So we use Kirchhoff second law. Okay, Kirchhoff second law. Okay, our Kirchhoff second law states that the total change in potential differences must equal to 0. All right, so find out in Google what is that Kirchhoff law, or actually if you subscribe to my channel, you can actually see I have this Kirchhoff law for my physics 150. So go ahead and go through the video if you are interested. Okay, I think it's better go and read through it. Okay, go through it. Now AB, because you hit the positive terminal, you lost kinetic energy. So that's why you have negative V. Okay, negative V. And then by the time you come here, current go to this direction, you move through direction. It's just like you're climbing mountain. So you do a positive work done. IR. And because only 2 components, 1, 2, so equal to 0. So that means your IR is equal to V. So now we're going to find the current. I is equal to V over R. But what is your V? Your V is this one, right? Okay, so 1 over R, and this one is V naught sine omega t. So your I is equal to V naught over R sine omega t. Now, since V divided by R is current, and the V is a maximum V, so you have a maximum current. Okay, so you see that our equation here compared to this equation, okay, you have to compare equation. They are in the same format, right? This is number 1, this is number 2. So since 1 and 2 are in the same function, okay, I mean same trigonometric function, so we say V and I are in phase. Okay, they are in phase. All right, so they are in phase. So that is what happened. Okay, that is what happened. So how do we draw in phase? How do we represent in phase? So we have to use something called the phasor diagram. Okay, we have to use something called phasor diagram. Yeah. So we go to phasor, draw the phasor diagram for our resistor. So we already know that they are in phase. So that means they should be pointing in the same direction. So phasor diagram for resistor. Okay, our phasor diagram for resistor. So our phasor diagram is more or less like our coordinate axis, x and y. Actually they are. Okay, so now I'm going to use the blue color for the voltage, the red color for the current. So our voltage normally is vector is much longer than that one, so we choose our 0 here. So when voltage is here, okay, when the voltage is here, okay, I call this one VR. Okay, and then orange color is for the current. So the current and voltage are in phase. That means they point in the same direction. Okay, they will point in the same direction. So that is our IR. All right. So that is how you represent two things, the relationship between voltage and current, okay, using diagram like this. So this is called phasor diagram, okay, PHASOR, something like a rotating vector. All right, so next one, okay, next one we're going to come to what we call that, the what is that already, capacitor. Okay, the next one is B, capacitor in AC circuit. Okay, capacitor in AC circuit. So now we have a same AC power supply. okay, and then we have a capacitor connected to the power supply, and our power supply again is actually the same, okay, AC, and then we have two parallel lines representing the C value, okay, the C value, and the power supply here is V equal to V0 sine omega t again, and the current is I, okay, current is I, but here there might be something different. Let's assume you have this positive and negative, right? Okay, positive and negative. So what happened here is when you connect a capacitor to the power supply, the terminal of the capacitor that is connected to the positive one will become positive and this one negative. Alright, so what happened here is if you connect a voltmeter like what we did for our resistor, you're going to have a voltage across the C, okay, across the capacitor, so we call that one the VC. Okay, now if you look at it, this is actually more or less like a battery, okay, more or less like a battery. So now we're going to find the relationship between the V and the I, like what we did for our resistor. Okay, hopefully we can use the same effect here. So we're going to start with A, B, C, D. Again, we use our Kirchhoff law. Okay, so I will now use Kirchhoff's second law. So I use short form here, Kirchhoff's second law. Start from here to B, B to C, C to D, D, go back to A. Since there are only two components, so you only have two terms, right? So according to Kirchhoff's law, the total change in potential difference must equal to 0. Okay, so now we start from A to B. Again, this one is negative V because you hit the positive terminal. The V is this whole thing here. And then come to here, you hit the negative terminal, become plus VC is equal to 0. So your VC is equal to V. Okay, but what is VC? Our VC, okay, our VC, okay, but V for a capacitor is equal to the charge on a capacitor divided by the capacitance value, this one. So I'm going to put this one in here, okay. So our Q over C is equal to V now, and our V is V0 sine omega t. Okay, V0 sine omega t. Alright. Okay, are you lost now? It's okay. A lot of people will get lost, including me in the first place. Okay. Now, Q over C. Now, we can actually put the C over here now. So, Q is equal to C V0 sine omega t. Alright. So, what's next? What's the next thing now? The next thing is, we want to know current, right? But what is charge related to current? Okay. So, now again, current is equal to dq dt, the rate of flow of charge. This is the differentiation. So now we can have to differentiate this thing, see what happens. So current is the differentiation of this charge against time. Okay, so now we can differentiate. We take out the CV0. When you differentiate this, you get cosine omega t, and then differentiate internally, you get omega. So now we take the omega out, it becomes omega CV0 and cosine omega t. So look at this equation. This is totally different compared to what you are given just now. Just now you are given this, right? Okay, so I'll call this equation again number 1. This is number 3 now. Okay, same like just now we have this is number 1, 2, and now this is number 3. So now if you compare number 1 and 2, they are totally different function, right? Okay, so what we want to know is we want to change this function back to sine. Okay, back to sine. So we have a trigonometry function, okay, something like this, from let's say cosine A plus minus B. We see what do we have. Okay, we see what do we have here. Cosine A and B. What is that function already? Cosine A and B is equivalent to something like cosine A, cosine B, and then minus plus sine A, sine B, right? Okay, sine A, sine B. So now, how can we get so that our answer is only sine omega t? So let's assume our A is omega t. Okay, let's A equal to omega t and B is equal to pi over 2. Well, don't ask me why, because my lecturer taught me like that also, so I teach you the same thing, okay? But of course, they already tried something else, and then tak jadi. So this is the only way to solve the problem. So your cos omega t plus minus pi over 2 is equal to cosine omega t and cosine pi over 2, and then minus plus sine omega t and sine pi over 2. Now if you look carefully, cosine, this one becomes 0 and this one becomes 1, right? So finally you end up the whole thing 0 and you only have minus plus sine omega t. So this one is an extra thing for you to look at. Okay, this is an extra thing for you to look at from the point of mathematics. All right, so maths are different from physics. Yeah, okay, maths are different from physics. So okay, now if you look at this, how to change this, okay, into this, okay, how to change this into this, okay? So it seems like we don't have, right? Can or not? Can we change or not? We cannot change, right? We cannot change any one of this into this. So this one, okay, we know that there is a relationship between sine omega t and cosine this one. Now we go to another one, okay? Now from sine a plus minus b, what do we get here? This one we're going to get sine a cosine b plus minus cosine a sine b. Okay, and then do the same thing like what we did just now. Let a equal to omega t, b equal to pi over 2. So our sine, okay, our sine becomes sine omega t plus minus pi over 2. So what we get is sine omega t cosine pi over 2 plus minus cosine omega t and sine pi over 2. So again, same thing here. This one is going to become 0 and this one become 1, right? And we simplify the equation, it become only cosine plus minus cosine omega t. Okay, plus minus cosine omega t. So that means, means what? That means we have found something that is similar to this one. We can change this into something related to sine now. So this is our second part, okay? Our second discovery. Of course, in exam, you don't have to do this, okay? You just memorize. I think memorize is worse than this, right? Okay, we know that our final answer for our I, okay? See, from I here, from I equal to omega c v naught and cosine omega t. We know this cosine omega t here, positive cosine omega t, can be replaced by this one. If we choose positive cosine omega t, we can choose so that it becomes positive pi over 2. So our current now become omega c v naught, and this one replaced by sine, so now become omega t plus pi over 2. So that is our current, okay? That is our equation for the current, okay? But we know that this is I max, right? I max, isn't it? Okay, I max. So I max is what? Okay, but I max is equal to omega c v naught, isn't it? So now what happens if you divide, okay, v naught by I max and move this one over here? V divided by I is what? This one is resistance. This is a resistance, okay? This is a type of resistance for what we call that, okay? For capacitor. Okay, a resistance of capacitor, and we call this one chi C, okay, reactant. So this is called capacitive reactant, okay, capacitive reactant. So our capacitive reactant is this one, 1 over omega c or 1 over 2 pi fc. Yeah? So this equation you have to memorize, okay, you have to memorize. So if this equation just now from number 3, this one will become number 4, and this is our number 5 discovery here. So now from number 4, we write down the equation. It now become I naught, right? The whole thing is I naught sine omega t plus pi over 2, and compare with this one, v equal to v naught sine omega t only. Now, by comparison, we know something is different. I and V are not in phase. Okay, I and V are not in phase. Okay, so what happened here? If you have plus, meaning that I is actually faster than voltage. So conclusion from here is, from this comparison, when this one plus pi over 2, meaning that I is moving faster or increase faster than the voltage, is leading ahead, okay, leading V by pi over 2 radian. Okay, you can say it like this, or if you like the negative way of saying it, you can say V is behind the I, or we say lagging, okay, lagging I by pi over 2 radian. It means the same thing, okay, it means the same thing. So that means when you have a capacitor in an AC circuit, your current increase slower, your current increase faster than your voltage. Alright, so that is a funny thing about capacitor. The next thing happen also to inductor. Alright, so for this capacitor here, then you see that you have two conclusion here. Number one is the I leading V by pi over 2 radian, and then another one, by looking at the equation here, we get something like this. So we know that capacitor actually has what we call that resistance, and this resistance, if you look carefully, it depends on your frequency. Okay, it depends on your frequency. So now this is our page number 3. So now we're going to look at what happened when we increase the frequency for the capacitor. Okay, so we look at this one here. Okay, we plot our chi C against frequency F. Because it is inversely proportional, so what we have is, you're going to have a graph that looks like this. Okay, when the frequency increase, okay, your reactant, okay, the reactant decreases, okay, decreases. All right, so that is our parts for our capacitor. All right, okay, next one is even more interesting. Now is the inductor L in AC circuit. Okay, oh yeah, forgot, we supposed to draw the phasor diagram, right? Okay, so we go to the phasor diagram for capacitor. Okay, capacitor. Now phasor diagram, we start with the axis here, the phasor diagram. For capacitor, okay, phasor diagram for capacitor, we have the vertical axis and the horizontal axis. Now we know that our voltage, okay, our voltage is always, our current should be always in the same direction, right? We start our current here. My current, I use red color, I think. Okay, red color. Here. This is, current is orange color. Okay, current is orange color. So my current is here in this direction all the time. Okay, so this is a IC. Okay, current for that one, and then my blue color, okay, is for the voltage. Okay, is for the voltage, the blue color. So since your voltage is lagging behind, so it is here. Okay, lagging behind, because you start from here, behind should be here. So this is our VC. Okay, VC. All right, so that is the phasor diagram. So they are 90 degree, right? Pi over 2 radian. So this is pi over 2 radian. Okay, compared to this one, you have something else. Okay, you have something else. All right, now next one. The next one, C, is our L in AC circuit. Okay, our L in the AC circuit. All right. Okay, L in AC circuits. So we have this power supply. And we have inductor. Okay, we have inductor. and this inductor like this. Okay, now we will assume our current to be this one. Okay, we start with current like this. It's easier for our mathematical manipulation later. So the current here is I naught. Okay, I will choose sine. Okay, sine omega t. Okay, so our V we don't know lah. Okay, with V we don't